Hey guys, welcome back. We're continuing to do power factor correction. We've learned how to do power factor correction to unity, and now we're going to learn how to do power factor correction to 90%. A little bit different, but the same, okay guys? And this particular question that I'm going to do with you is Unit 5, Handout 6. It's the first question there, okay? And we're going to do it together. All right guys, so let's look at it here for a second. It says it's a single phase 208 volt 60 hertz motor. It's drawing 20 amps at a power factor of 0.6. And then it wants us to calculate, excuse me, that's my, probably an email or something on my phone. I use my phone for all these, if you haven't noticed. Okay, guys? So, sorry about the notification. Usually I turn off my, ringer, but I forgot. All right, guys? So, single phase. It says calculate the capacitor required in VARs to correct the power factor to 90%, okay? And the reason we're going to correct to 90% as well as unity is because this is the minimum amount of correction you would have to do if you were a commercial or industrial customer and you didn't want to get a penalty for having poor power factor, okay guys? So we're going to correct this thing to 90%. And when you're correcting to 90%, it's the same as correcting to unity, okay guys? The first thing you're going to have to do is draw a power phasor diagram before correction, okay? So what I'm going to do here is write uncorrected, okay? And we're going to try to figure this thing out, and it's going to be the same as every, power phasor diagram. True power here, guys, VARs here, VA here. And we're lucky. Again, I've noticed that I've given you a voltage and a current, and so I can calculate my VA in this case. It's going to be the voltage times the current. It's going to be 208 times 20. So let me just do that for a second here. 208 times 20, okay guys, it's 4160 volt amps, okay, and it says the power factor is 0.6, and so now I'm going to calculate the power. It's going to be the VA times the power factor, so it's going to be 4160 times 0.6, all right guys, 2496 watts, okay. And the VARs going to be calculated using Pythagorean theorem, guys. So I'm going to do that quietly here. 4160 squared minus that answer squared equals root equals 3328 VARs. All right, guys. Now, you always want to finish this entire phasor diagram before you move on. So now that we've drawn an uncorrected power phasor diagram, and by the way guys, if I was correcting to unity, I kind of would be done already because my capacitor would be 3328 VARs and my VA would be equal to my power, which would be 2496. Okay, so if we were correcting to unity, we'd be well on our way here, but we're not correcting to unity, we're correcting to 90%. So now I have to draw a corrected phasor diagram here, guys. And the first thing I'm going to do here, guys, is draw my true power. That's the first phasor I always draw because I can never do anything about that. Okay, guys, it's always going to be there. And I'm also going to draw my VARs XL. Okay, my VA or my VARs, due to the inductor. And it's 3328. Okay, guys. Now, if I was correcting the unity, my capacitor would be coming down here and taking care of all of this, but I'm not correcting the unity, I'm correcting to 90%, so my capacitor is going to come down like this, certain distance. This is going to be my cap. It's not going to take care of all of the VARs XL. It's going to take care of some of it. And what I'm going to do is leave, 0.9 here. Instead of correcting this down to 0 degree angle, we're going to correct it down to 90% or 0.9, which is like 25 degrees-ish, something like that. Doesn't matter, okay? So this is what my phasor diagram is going to look like. And what we're going to do now is calculate our VA after correction, because I can calculate my VA after correction. It's going to be power divided by my power factor. And my power is 2496, and my power factor after correction is going to be 0.9. And this allows me to calculate, how much VA is going to be in the circuit after I've corrected it with this cap. Okay, guys? So it's going to be 2496 divided by 0.9. And it comes to 2773. Okay, so I'm not taking care of all the reactive power. I'm taking care of some of it. I'm going to leave 0.9 as my power factor. My VA is going to be slightly higher than my power, because I'm leaving some VARs in the circuit, basically. All right, guys, and so now that I've calculated my VA after correction, I can calculate my VARS X, which is going to be this right here. My VARS X is going to be the amount of reactive power that I'm going to live within the circuit. All right, guys? And it's going to be 2773 squared minus 2496 squared, okay? Because this is a nice little right angle triangle. So it's going to be the square root of 2773 squared minus 2496 squared. So I'm going to do that for a second here. Looks like I'm going to live with 1209 VARs, okay? And that is going to be the amount of reactive power in the circuit after I've corrected it. Now, this is not my capacitor, guys. This pink line is my capacitor. And so the capacitor that I'm going to have to stick in there is going to be the reactive power in the circuit that I started with minus the reactive power in the circuit that I'm going to live with. So that cap, guys, or I'll do it right over here, is going to be 3328 minus 1209. Okay, guys? And I'll do that here. 3328 minus that answer. It's 2119 VARs. Okay? And that is the answer to this. All right, guys? So to recap, what we did was we drew a uncorrected power phasor diagram. Forget about the capacitor. It's not in there yet. We calculated our VA. We know the power factor was 0.6, so we calculated our power and our VARs. And then we drew a corrected power phasor diagram. The true power is always going to stay the same. I'm still going to have all this reactive power due to the inductor. I'm taking care of some of it with a capacitor, and I'm going to leave a 0.9 here. All right, guys? And I can't figure out the capacitor yet because I don't know how much reactive power I'm going to live within the circuit. And the way I'm going to calculate that is to calculate the VA after correction. It is always going to be the true power divided by the power factor. Then use Pythagorean theorem to calculate VARS X. Okay, guys? And then your capacitor will be the reactive power in the circuit that you started with minus the reactive power in the circuit that you're going to live with. All right, guys? And I've had this as the answer many times, okay, where students are figuring this out. They figure out VARS X, and then they give me that answer as the capacitor size. But that is not the capacitor size. There's one more step. The capacitor size is going to get calculated by subtracting those two. Okay, guys? Now, as far as calculating how many microfarads that's going to be, this is going to be the same. Now that we've corrected it, it's going to be the same as, before. We're going to do it in two steps. We're going to calculate XC. It's going to be E squared over VARS. Okay? And the voltage is 208. And the VARS of the capacitor is 2119. Okay, guys? So I'm going to calculate that for a second. 208 squared divided by 2119. Okay, looks like that's going to be 20.42 ohms. All right, guys. And then the second step is going to be this one. C is equal to 1 over 2 pi fxc. Okay, and I'm just going to calculate that for a second. 2 times pi times 60 times 20.42 equals 1 over x equals, and it says it is 0.000129 farads, which is equal to 129.9 microfarads. Okay, so that is the answer for B. What would be the new value of line current, guys? Well, the line current after correction is always going to be the VA after correction divided by the voltage, okay? Because VA is equal to E times I. So I is going to be VA over E. And it's going to be the VA after correction. Now, if I was correcting this to 90%, my VA would be 2496, but I'm not. It's 2773. So 2773 over 208. Okay, guys? 2773 divided by 208. Looks like the current after correction is going to be 13.33 amps. Okay, guys? And this motor was drawing 20 amps. Now it's drawing 13.33 amps. If I was correcting to unity, it would be even less than 13.33 amps, because it would be 2496 divided by 208, okay? But we're living with some reactive power, so our VA is slightly higher than our true power at 90%, okay, guys? Now, here's the thing, all right? Let's look at D. Draw a schematic diagram showing the circuit components and the current flow in each part of the circuit. So I'm going to draw this for a second, okay, guys? And so here's my AC supply here. It is 208 volts, okay? And I'm going to draw my motor here, right there, okay? And I'm going to draw the capacitor that we added for power factor correction right there. Now, it's saying put all the currents in there. Well, we just decided that after correction, guys, that this thing is going to be 13.33 amps, and that is going to be the line current for the entire circuit, okay? And it's going to be right here, 13.33 amps, okay, after correction. Now, this capacitor here, it has some current flowing through it as well, and we know that this capacitor is 2,119 VARs, right? So this thing is 2119 VARs. And we can calculate the current in this part of the circuit because IXC is going to be VARs over EXC. And that's because VARs is EXC over IXC for a capacitor. So it's going to be 2119 over, EXC is the circuit voltage, right? Because it's in parallel. 208. Okay, and I'm going to calculate that for a second. 2119 divided by 208. Looks like it's 10 amps, guys, running through that. 10.19 amps through the capacitor. And I would measure that if I clamped on right there, guys. Now, here's the thing. This motor was drawing 20 amps before. Guess what? It's still drawing 20 amps. All right, guys? This motor does not know about this capacitor. And it was drawing 20 amps before I corrected it. It's going to continue to draw 20 amps after I correct it. All right, guys? And so I'm going to have these three currents here. I'm going to have 13 amps as my total circuit current. This motor is going to be drawing 20 amps, guys. And this capacitor is going to be drawing 10.2 amps. Now, you might say to me, Vanado, you've lost your mind. All right, guys? Because there's no way. I mean, I thought the total circuit current is supposed to be the sum of the two currents here. And I thought Kirchhoff said in level 1 that current in has to be equal to current out. And so somehow this 13 amps is feeding this 20 amp load and this 10 amp load. And the answer is yes. All right? Because here's what the phasors look like, guys. This 20 amps was lagging like crazy. So if I took a look at the phasors, the current phasors here for this particular circuit, guys, that 20 amps, it was a big inductor. So it looked like this, lagging. Here's the voltage, right? So this is going to be, I motor, and it was going to be 20 amps. Oops. Okay. Lagging a lot, and that used to be the total circuit current before I added the capacitor, but now I've added a capacitor which leads by 90, guys. So here's my cap. It sits right here. This is the cap, and its current is this 10.19 amps. 10.19 amps, okay? And the total circuit current is the sum of the two, the phasor sum of the two. So there's my I total, that blue line right there, I total. and it equals 13.33 amps. Okay, that one right there. So this circuit current, 13 amps, is the phasor sum of those two currents, that purple line and that brown line. Now we didn't correct it to unity, it's still lagging. That's because we only corrected it to 90%. If we would have corrected it to unity, guys, that cap would have been even bigger, okay? And the total circuit current would have been even smaller, and it would be completely in phase. All right, guys? But it's still lagging a bunch. All right, guys? And so that is actually what's going on with this particular circuit. Now, I'm going to do another one of these, all right, just for fun. Make sure you're good to go, but stick around for that one. All right, guys?